So monitoring is what we've mainly talked about at this meeting, making measurements with BAMs and reference grade monitors and sensors, typically at a specific point over time, or mobile monitoring or whatever, but it's still sensors, physical sensors. Modeling is where you try to take algorithms to predict what the air quality will be, maybe based on some monitoring to begin with. And the land use regression modeling was a perfect example of that, where they took a bunch of data that was made from the monitoring, and then they found some relationships to allow them to predict what the air concentration would be at another location.
Okay, thanks, Steve. So moving on, I think that's the definition for the monitoring and then the differences between that and then the modeling. The monitoring has got to do with measurements to determine the concentrations at a particular place and then a particular time. And then we can also, based on the measurements, determine human exposure and fluxes to the surface, that's land or water. Now for the modeling takes into account measurements as well, the ground-based measurements and then other measurements, merge them together to develop the model. But then that's based on numerical modeling, numerical calculations to solve mathematical problems. Now, with the monitoring, because, for instance, if we install a sensor here, how far is it, the concentration levels, how far does it go or does it reach, the spatial resolution? It's a bit quite low, and so that's where we employ the modeling to fill in that gap, the spatial representation. And so that's kind of the difference between the monitoring and the modeling. Now, we cannot say one is better than the other, but however, they complement each other to make each other more accurate, for accurate assessments. Sorry. And then these are the building blocks of air quality forecasting, or an AQ model. So it takes in an input condition, that's an initial condition, where we make use of meteorological data. It incorporates meteorological data, land use, such as the terrain, emission inventory, and measurements from the various monitors. That's all various, that's the ground-based satellites, and then the other sources of measurements. So then once we incorporate that into the, that's the initial, we set that as initial conditions, and then try to use mathematical equations to solve, numerical solutions to solve these mathematical equations. That takes into considerations most of the laws governing physical and chemistry and chemical reactions. We then are able to assess mitigation strategies from some of these models, and also it helps determine the causes and then patterns of air quality or air pollution effects. And then based on that understanding, we are able to inform policy and then public awareness. And so moving on to the techniques associated with model, like I said, it takes in an initial condition, and then the current meteorological, that's from the current meteorological conditions based on weather forecasting, and also some chemical reactions from chemistry, including the current condition of air pollution concentration levels. Input that into a set of mathematical equations, and then the output is a forecasted air pollution concentration. And that's basically what I have listed here. So an input of current air quality, an input of forecasted weather parameters, a model of pollutant emission, and then giving out a daily or hourly forecast. Most forecasts for better accuracy last for 2 to 5 days for better accuracy. Now, how do we determine which air quality model to use at which time or over a certain place? So these are the various choices, points to take into consideration when selecting a model: the size of the study domain, availability of input data, that's the weather data, and then also the chemistry or the chemical data, the chemical concentration, and then also the whether chemical reactions are relevant or not. So we take those things into consideration before deciding on which model to use over a particular area. Now, they are based on various categories. We have the categorization based on the type of chemical components. That's either the components are reactive or non-reactive, so such as the and NOx, which Dan showed on the first day, they are reactive in the sense that when they are released into the atmosphere, they are able to react. They undergo photochemistry to break down and then form ozone. And then the non-reactive gases such as SO2. So what are we determining? That will help us determine the type of AQ model to be employed. And then also we have categorization based on emission sources. That's the point source, the area source, and the line source. Point source has got to do mostly with industries, and then the area source are basically used for predicting or used for forest fires, the dust storms, and the rest. And then we have the category based on modeling approach. That takes into consideration the box model, the Gaussian plume, the Eulerian, and then the Lagrangian. Then we have the category based on temporal scale. So we look at, okay, at which scale, when we are trying to model a certain output, we determine at which level we'd want to reach. That's the spatial extent. And so for this slide, it explains the types of scales we have during AQ processes. So we have the macro scale that takes into account the global forecast. That's on a global scale. And then we have the regional, that's basically on the continental scale. The local has got to do with a country. That's if probably I'm modeling over a country. And then we bring it down, we scale it down to city level forecast, which are much more finer than the global scale forecast. Now, these are the types of the AQ models. Raphael talked about statistical modeling, so I'll not go into that. The hybrid has got to do with a combination of the two, the deterministic and then the statistical. So I'll focus on the deterministic. Now, on the deterministics, they use numerical solutions to solve mathematical equations that describes the various laws governing physical and chemical processes. And then, as such, models in general are divided into AQ or provide us with AQ assessments and then AQ forecasting, and so does the deterministic models. Next slide, please. Okay. So here are some applications of AQ models. We had Francis Pope talking about source apportionment. So models can aid in source apportionment, environmental impact, and then the real-time forecasting and the others. Now, why the need for forecasting? The models help us predict what will happen tomorrow, today. So that's the basic understanding of forecasting. But then forecasting takes into account initial conditions. And then also through modeling, we can equally get the air quality index. That's an indicator developed for us to know how polluted the air currently is at a particular time. Now, why the need for forecasting? We've heard so much about the harmful nature of air pollution when we inhale particulate matter and all. And so these are some of the diseases associated with poor air quality, cardiovascular diseases, stroke, and the rest. And so once we are able to give accurate forecasting, it can lead to ease in planning our day-to-day activities, and then also help to assess the risk associated with the environment and climate as large. Now, when we forecast, what do we get out of it? It helps us to give health alerts to the vulnerable population in general. It also supplements existing emission controls. And then operational planning, when we are talking about haze, poor visibility, which can impair aviation activities and also other commercial activities as well. And then it aids in emergency responses. But then there are some challenges associated with forecasting in that some meteorological conditions can affect the forecast we give. So probably if I forecast for the air quality for tomorrow, if there's a temperature inversion happening tomorrow, it might affect the quality of forecast I have predicted, which I may not have seen earlier. So that might be a bit of a challenge. And also, models are a bit computationally expensive in the sense that it requires very fine computational mesh, and then that requires high resolution mesoscale weather. So based on all these, we are trying to develop a forecasting tool for use over some selected cities in Africa. We have Accra, Ghana, Nairobi, Kenya, Kampala, Uganda, and then I think those are the three I remember. So that's under the Canary Islands, which Carl has already talked on. We are evaluating the GeoCF model output with ground-based observation data, and then trying to correct the bias. So we can use the forecast, the bias corrected output as forecast over Ghana. Now, Carl has talked about the GeoCF, and this is the how it's built. It's based on the physics aspects, the chemistry, and then we get the output, the composition forecast. The forecast, it gives a 5-day forecast, and with a 1-day replay, spatial resolution of about 2.5 by 2.5, and then we have the 15-minute surface data and 1-hour average data coming from the GeoCF. This is the overview which Carl already showed. Mine is not in animation mode, but then this is a general overview of how the model output looks like. And also, you can access the various data, which is open source, the data from the model at the site. So for the Canary Islands, so we have Kigali, Rwanda, Kampala, Accra, Ghana, and then Nairobi. We couldn't do for Kumasi. This is the workflow of our work. We take ground-based measurements and then try to use that to evaluate the model output. Then we do some data cleaning, and we use machine learning to correct the bias between the data. Now, our result is to obtain a robust forecast for these cities over Africa. And also, we evaluate the output from the forecast to maintain good scale. So these are some of the results we are getting from the analysis. This is at the initial stages where we get data. I'll concentrate on the BAM at the US Embassy because that's what we've developed the bias correction for. At the US Embassy, there's a reference grade monitor there, the BAM. That's what we use the data from the BAM. And then we try to downscale the model output to get the exact point source as the BAM, the data as the BAM, and then try to compare how the GEOS is performing against the ground-based data. However, we saw that there was some bias, some underestimation. And in April, the data, the GEOS overestimated the ground-based data. And this might be due to the fact that once the GEOS, that's a limitation of the GEOS anyway. Once it sees or it detects smoke, it assumes that it stays there for the next 5 days. So probably during that time, as we are preparing for the bush burning and all, maybe the model might have detected some smoke, and then so the overestimation over there. But then here is when we corrected it. So we use the XGBoost model algorithm for the correction. Now after correcting, the observation is in red, the model without the correction is in gray, and then the model plus the correction is in black, and you could see clearly how it's performing after the correction. Similar thing is done over Kampala, a site at Kampala, and also you could see the improvement after applying the correction to the model. Now, for the next steps, we are trying to evaluate the bias corrected forecast we have gotten out of the work. So, however, the data we had, there were still some inconsistencies with the ground-based data used in validating the corrected output. And so we are still working on it to make sure we get a final result. And these are some of the challenges that we encountered. At the end of the project, we expect to see something like this, an interface like this, where you could click on Accra and get a corrected or accurate forecast over Accra, AQ forecast over Accra, and the other cities. Now, this is the link to the GeoCF model, if you would want to access it. These are the layouts or the outputs you get. The data access, you can access the data at any of the links there. It's open source anyway. Here are some references, and thank you. I hope that was short.